Okay. All right, let's get going. Okay, so web map architectures this week. Yep. What we need to know is cloud computing. Okay, so what have we done? We've seen the internet, the World Wide Web. We know roughly reasonably well, hopefully, what they are, what the difference is between them, how they work. We then, change this light. Then we looked at web map, Croc's web map classification, which, as I say, I've got issues with, but I think it's still quite useful exercise. But what it does do, I think, is highlight some different aspects of web pages, what their use is. So some of these classes in Croc's classification are to do with use or purpose. Others are to do with the functionality, how the actual maps are delivered, how you can interact with them, that kind of stuff. And then I've sort of said, how are they delivered, which is to do with the computer architecture that's used to deliver the maps. Are they dynamically produced? Are they harvested from different distributed locations? Is the data being pushed through in real time? And basically, this lecture is about this third section. How do we actually deliver maps over the World Wide Web? That's basically what today is about. Now, of course, I've just run over here from writing practicals and other practicals, so I'm ill-prepared. But I thought we'd have a quick look at the Magic site, but I can't do it because I still haven't got this capturing anything else but PowerPoint sorted out on the laptop. But if you've not come across Magic, I mean, you've seen enough web mapping sites, I don't need to show it to you. But I would advise you, it's a good one to know, especially for the UK, because it provides a sort of one-stop shop onto large amounts of environmental data for the UK. So you can do things like see national nature reserves, you can see land use classifications, you can see SSSIs and things like that. And what it is it's produced by DEFRA, the Department for Environment, Food, something or other like that. I can never remember exactly what DEFRA stands for. It used to be MAF, Ministry for Agricultural, Farm and Fisheries, and it's now DEFRA, whatever that stands for, lose track of it. But it collates information collated by DEFRA, Environment Agency, English Nature, various organisations like that. Anyway, it's well worth a look. It's a good example of a sort of web mapping interface. So taking Magic or any other web mapping application, what's it made up? What are the components that are required to build such an application? Well, data of some variety. Now, that data may be stored locally in relation to whatever system application we're talking about. So perhaps, and I don't know whether this is true for Magic or not, but they have some local repository, maybe of DEFRA data, a local store of data. But they also almost certainly access remote data that's being provided, served out by other organisations, for example, the Ordnance Survey base maps. Now, I don't know that Magic does call the Ordnance Survey maps from the Ordnance Survey website to display in the Magic Win application. It may be that they've got a copy of the Ordnance Survey data stored locally, which they then serve out. They may work that way. But for applications, web mapping applications, you've either got data locally or you've got data remotely or you've got both. You've got the various functionality that it supports. So it allows you to turn off on layers, you can make them transparent, you can zoom in, zoom out. It also supports personalization of your maps, so you can put a title on, you can draw things on top, draw graphics on top like that. So it's got overall this functionality, and that functionality we can partition or is partitioned into two locations, so that there is some of that functionality, or the functionality required to deliver that mapping application, goes on the magic server, and I'll talk a bit about servers in a minute. So when I use that magic map, I do something on the screen that sends some kind of request to the server, the magic server, which then processes that request, maybe extracts more data out of the database, sends it back to me. That update, that change is then sent back to me as the client. My client computer then has to process that and decide what to do with it. So the functionality is distributed both remotely on the server and also locally on the client. And the final thing we need is an interface, that covers the arrangement of objects and tools on the page, the styling, any help, stuff like that. So in this case, we're mostly going to be considering these two parts. We're not going to do the interface comes later. So the components these components, and I'm using the word components in a very general sense here, but the components required to deliver a web application have to be arranged into some kind of computer network architecture or just architecture. What is a computer? Well, we know what computers are, don't we? They're little boxes with screens and keyboards and things like that. It's actually quite hard. There's no good definition for what a computer particularly is, or I haven't found one that I find particularly nice and easy to understand, but basically it's some kind of device that accepts information in digital form, processes it, and puts some kind of output. That's about the best definition we get. But the point I want to make is that computers, of course, are a lot more than just the things that we classically think of, keyboards and screens and boxes. They obviously include tablets, although my son keeps telling me that is not a computer, that is a tablet. I slap him hard, but he still repeats it. He'll learn eventually. Mobile phones, again, computers of various kinds. Game consoles, they're just computers. You can program them to do just like you can a program. Increasingly, computers are getting spread out into things like cars, and I keep mentioning smart houses and controlling your temperature in your house and your fridge and things like that. So computers are not just your standard computer. There are all these different types of devices. They're increasingly embedded in things that we don't think of as having computers, like cars, or don't immediately do. They are also increasingly looking like this: large data centers storing vast amounts of data, doing huge amounts of parallel processing, often located somewhere in the Midwest of the United States, well away from sort of nuclear blast zones and earthquakes and things like this. This is one of the Google centers. Quite like this photograph showing just the amount of energy and heat produced by these centers. They are huge consumers of electricity, and it's an environmental issue, the amount of heat and energy used by these locations. So computers cover all these different kinds of things, or all these different kinds of things are types of computer. The network, so we've got computers and other bits of hardware. We've also got our network that they're connected into. Just a little diagram to show us what a network is. It's at the most general level, we can represent a network as a set of nodes connected by edges. The nodes in the internet are the computers, the hardware nodes, the routers, the other devices attached to the network. The edges and links are the physical cables that connect these devices, but also any wireless links between them. Computer networks, not surprising. Finally, architecture. Well, architecture is simply the words we describe to describe the arrangements of parts that together create some kind of complete design. So a computer network architecture is arranging the components that we need to create our applications, the arrangement of those parts in a network. We need to consider two kinds of network architectures: hardware architectures and software architectures. We know what the hardware architecture is, just simply the relationship of components and other hardware. Software architectures are the arrangement and relationship of the software protocols, programs, and other programs that work together to create your solution. And of course, these sit on top of and have to operate on a particular hardware architecture. Now, the hardware, you may not need to consider a great deal about the hardware architecture for many different applications, but it's still, any software application is still obviously running, has to run on some kind of hardware architecture. So, in the beginning, there were no, or there are still unnetworked computers for particular reasons, security, just being old, people not having networks. So if we don't have a networked connection, we have to copy. The only way we can get information between the different computers was by physically copying, either using various physical media. Obviously, you're all familiar with USB drives, DVDs still about, floppy disks. Increasingly, I think some of my first years wouldn't know what a floppy disk was. Didn't even know they probably existed, but we need to copy the data physically onto some kind of hard media, and then move it towards the computer. All very well, but time-consuming and prone to read-write errors, particularly when you're dealing with the days of when you had a stack of a program or a set of data on 20 floppy disks. You probably had a 50-50 chance of those 20 disks all reading correctly into the other computer. So there's time and effort involved, and of course you're making duplicates of things, which may or may not be a good idea. As we know with data, it's not a good idea. So we start to, it's better if we can directly wire the computers together so that we can communicate directly between them without any need for intervening physical media and human interaction. And the simplest architecture or the basics of just about all computer architectures is the idea of the client-server system. And this is about the simplest architecture you can have. So very simple, you have your user works on what's called the client computer. So here am I, I'm working on this computer, it's the client. It's running a web browser or some other program that I'm using. I do something on my client computer, on the program I'm using on my client computer, that needs some kind of information from somewhere else. So it sends a request to the relevant computer that's got the information, the data on it. That's computer that the request is sent to is called the server because it's there to serve you. It's sitting there listening for people making requests, other computers making requests. It gets a request, processes that request in however formal manner it does, then it replies with some kind of response to the client computer. The client computer then updates its screen, does whatever it needs to do with that response, feeds that information through graphically to the user, who then carries on as the cycle starts again. And that's what you're doing, I have been doing in the last part of the module with pgadmin 3 and Postgres. You've been using a client-servant architecture, but it's not been a web architecture, it's been a database. You've been doing it in a database architecture. So you've been running what's called a standalone client server. Basically, you're running the server is running on the same computer that your client is running. So Postgres is running as a Postgres service. It's running on as a local host, so it's running as a service on the local host. You open pgadmin 3 on the same computer. You type in your SQL query. You connect to the database. You type in your SQL query, it pumps that SQL query through to Postgres server. The Postgres server processes it, then returns the query to you. So you can have a client-server architecture running within one computer. It doesn't actually require two computers at all. Many small offices, organisations in places like the Kingston University operate their offices on a sort of client-server type architecture. So in this case, we've got one file server, main file server, and then however many PCs and other devices attached to our local area network. Perhaps we're running Postgres on our file server. All these different users can access Postgres through the network. They're all accessing the same database, the same version of the data. Therefore, we've not got problems of data duplication and shifting and the differences that build up between copies of data. So client-server net architectures work within local areas. This is how most local areas work. Area networks work. The internet is basically, we can regard that as a client-server architecture. Instead of the intervening transport network being a local area network within a building, sort of an Ethernet cable, it is the great internet, and we rely on TCP, IP, and HTTP protocols to navigate our requests from our client computers through the internet to the server component and then back again. So, the World Wide Web. So the World Wide Web, as we know, uses the HTTP protocol to exchange data across the internet. So, here am I on my client program. I'm running a browser, web browser, and as you can see, I'm looking at a Facebook page. I've just loaded up a page. It happens to be Facebook in the picture, but it doesn't really matter. That page, so when I type the address into the page bar there, what it does is it creates an HTTP GET request, which gets sent across the internet, the network, to the server. And the server, of course, is identified by the DNS name, the domain name in the URL. That gets posted to the computer with that domain name that's identified by that domain name, which of course maps onto an IP address. When an HTTP GET request comes into that computer, it sees from a sort of a part of the header file that arrives, this is an HTTP request. And what happens is that the computer is configured so that HTTP requests coming into that computer are directed to a web server. In this case, it's Apache, but it could be Tomcat or one of the other web server programs. Basically, there's a little sort of a inbox here, and it looks at all the requests that are coming in, and it says if it's HTTP, we're going to send it to Apache. If it's FTP, we maybe do something else. If it's a different kind of protocol, we're going to do something else with it. But if it's HTTP, we give it to Apache. Apache then looks to see whether, if it's just the URL of a web page, it looks to see whether it can find that web page. And if it can, what it does is it return that with what's called a post. So it posts that back to the client's machine. That's picked up by the internet browser, and the internet browser processes the response and displays it on the screen. If the page can't be found, you get a 404 error replied. Hence the name of the number of this module, 7404. That's why we chose 404. Okay, now in general, what's coming back on the post is, as we know, web pages made of HTML, CSS, and perhaps some JavaScript or some programming embedded in as well. But these HTTP requests can return lots of other things as well. They can return any type of file you like. So it might send an image file back. It might send a video file, audio file, or indeed a data file back. So it's not just, HTTP is not just for HTML web pages. It's for every type of file format. And as you probably know, we can have pages that include images and things like that that come from multiple servers. So we can have a web page that is effectively the contents is distributed across different servers. So for example, we have a web page, we maybe make one call to the web server to get that web page. That web page is then returned to the browser, and then it contains the URL. It contains an embedded image which is on a different server. So a second HTTP request is pumped off to the second server, which then returns the image which is embedded within the web browser. Now, to be honest, I'm not sure whether it happens like this, as I show, or whether it sort of happens like this. I don't actually know whether it happens like that, but ultimately it doesn't matter. That's a schematic conceptual diagram of what's going on rather than being 100% what happens further down the system. So that's very simple. But many, many web pages are not just written hard-coded in HTML and put on the servers. They're in fact dynamically created on request from using a computer program running on the server. So some kind of server program written in some language like PHP. PHP stands for Personal Hypertext Processing Language. We'll meet that later on. So this is just a program that runs on the server. So in this case, so for example, this is things like eBay. You've just typed a request on eBay, you're searching for something, the wife wanted a new mobile phone the other day, so you have to type the mobile phone onto eBay. It goes off to eBay, then it has to query the database for eBay to find out what mobile phones are up for sale or whatever to return the information. The web page, they have no static web page that has all the mobile phones for sale at any particular moment in time. That's too much effort. So in this case, we kick off our HTTP request, gets shot off to the Apache web server. The web server, in this case, sees that it's an HTTP request, but instead of having a .html extension at the end, it's got a .php extension, which means it's a PHP program. So Apache gets that, sees that it's PHP, finds the PHP program running that's named, runs that query. Now in this case, that query is going to, that PHP program connects to the database, pumps the SQL, writes the SQL that's required to extract the relevant data out of the database, pumps that SQL into the database. The database pumps back the results to PHP, and then the PHP program takes that data and writes the HTML page to return on the basis of the data that's returned. And the instructions that are received, that gets sent back to Apache, and then that gets sent back to the browser. So in this case, there is no HTML page saved anywhere. It's dynamically created on demand using a program and a database extract when required. And in this case, we're still returning a web page designed by the supplier. Okay, this is probably not very... Okay, so that's an example. I'm just checking where I'm going now. Okay, so that's an example. That's showing you the most basic sort of web architectures. Basically, everything else is sort of variations on this kind of thing. Okay, so that's sort of looking at things from a process level, sort of, what's going here, what's going where, exactly sort of tracing a particular request through the architecture. But when we're designing systems, and I think we'll meet this again later on, what we need to decide which bits of functionality, and the functionality is derived from the various components that we have. So different components give us different types of functionality. we have to design and decide where this functionality is going to occur. Is it going to be done on the server? Is it going to be done on the browser? Is it going to be done in the database? So when designing architectures, quite often people design them in what's called layers. They arrange these components or these modules into a number of different logical layers, just like we have a sort of logical design model for databasing. This is a sort of equivalent for logical model for how we position these various components in our architecture. So each of these modules or components is an individual independent piece of software that does a distinct function. And what we tend to do is to place modules that perform related functions in the same logical layer. So this is how we draw diagrams to understand the architecture of systems, or this is one of the ways in which we draw these diagrams. And probably the most common architecture, the diagrams that you'll see, are called three-tier architectures. Here, this is an example. There are three different tiers here. We are talking about, we have a data tier, which is where the data is stored. So databases, file systems, the sort of data level. So in this case, we've just got one database, but there may be, of course, several different databases. There may be, and these data, you might have a relational database, but you also may be accessing some NoSQL databases. Maybe you're accessing a whole load of raw images on file as well, and that's a data store of some kind. So you can identify your data sources at one layer, at the lowest layer. Then at the next layer up, we can draw or include the modules and things that are involved in the logic of the system. So the logic is the system, is the functionality, how we do things, the components that we need to do things. So we have a logic layer, and as I say, some of that logic, sometimes you see the logic layer divided into two layers, server logic and client logic. That's not unusual to see that logic layer divided. And then at the top level, we can have, in this case, we've got a presentation layer, a layer to do with the modules required to display the information to the user as well. Okay, so that's that's a schematic. What do they sort of, we'll see what they actually look like in a moment. So, I'm just going to show you this example. So, before I worked at Kingston, my last job, before I became a lecturer, was writing, or I did write, this web application called the Entangle Bank. I'm going to talk to you quite a bit more about this and its history in another lecture. But basically, it provides a web interface onto a variety of biological data sets, primarily the range maps for all mammals, a database of abundance time series for mammals and other organisms across the planet, a database of the traits of mammals, how many offspring they have, how large they are, how much they weigh, how long they live, that kind of stuff. And two trees, a taxonomy and a evolutionary tree. It doesn't really matter about them. And I built this interface, this web-based interface that allows you to query across these different data sets. So it supports spatial queries, attribute queries, tree-based queries as well. So sort of, this isn't quite a three-tier diagram. It's a bit of a botch, but we do have a database layer. It's running on Postgres underneath. I've got various tabular data. I've got the geographic data stored in PostGIS. I've got what's called a PhyloDB schema for storing networks and trees. Then I've got another sort of custom-built schema for this time series data, and some other bits and bobs as well. So underneath we have a data layer. Then I have this web interface, which I showed, which that's the main front page that's on top of that. That is written It's mostly written PHP server side. It's got a map interface, JavaScript map interface, which will be running client side in open layers. And we also use the GDAL OGR file translation program, which you should be aware of, to do translations between geographic formats. This is what the main query page looks like. So you can search on biological names, trees, attributes, geography, and time. We won't worry about the details of this. As you can see the diagram, so what you do is you click on one of these. If I'm going to click on the geography one, it brings up the geography query window or page. This is an error I haven't been able to fix. I need to fix that, so ignore that. That shouldn't be there. But it brings up a little map interface. This is using the Open Layers library. It allows the user to draw polygon, put a line or a set of points on the map, and then those go through and can be pumped through to a spatial query, so I can find all mammals which have ranges that intersect or are within this polygon that I've drawn. Okay. When I've set up my query, then I can press the Run button there. When you press the Run button, it sends the query, the present query, off to the server. The server does the processing and will return back the results. And you will go back to the home page like this. I don't actually have a slide here, but you'll get a series of the queries. We'll build up a chain of queries and the results from those queries displayed on this front screen. So what does it look like underneath? Well, this is rather, I think I can draw a better diagram than this. Sorry about the state of it. It's one of these things that needs doing. So overall, we're looking at just considering this mapping interface here because we're interested in maps as opposed to other things that are part of this application. So I've got a database layer, this bit down here, which is on my host, my local host, which is running Postgres. The local host in this case is an Imperial College server somewhere in South Kensington, presumably. So here I'm running my Postgres database. I've also got, obviously, on our local host, we've got an Apache server, web server running. And this is also a set of PHP programs that run server-side that basically write these web pages. So this page is written by PHP program. All those web pages that you see are written by PHP programs. So the web browser, the person on the web browser makes a request to the Entangled Bank. It kicks out an HTTP request. That's picked up by the Apache server. The Apache server runs the appropriate PHP program. Now, depending on what the user is trying to do and what type of HTTP request comes in, the program will do different things. The PHP program will do different things. If it's an actual database query, perhaps I've just drawn that square on the map and I've pressed run, then the PHP program will take the parameters that are passed in the URL, and I'll talk more about parameters being passed in the web address, take those parameters, turn them into an SQL query with PostGIS functionality, obviously with post-spatial queries, pump that query into the database. The database will return the results. Then the PHP program will update the HTML page, will write the appropriate sort of response page and send it back to the web browser, to the browser. If the request was to display the map selection page, so this page here, which includes the embedded map, then also what gets sent back is the JavaScript program for the Open Layers map. The JavaScript program goes back to the web browser and runs within the web browser. Part of that JavaScript program says display this base map. This base map is a Google map. So it kicks off a request from another HTTP request, but this one to the Google Maps API, which has an underlying remote server, Google Cloud database or whatever underneath it, returns the underlying map, base map, which is then displayed in the open layers window. If I'm asking to download data, because the application allows you, once you finish doing querying, you can download all that data, and you've got the option for spatial data, you've got the option to download it in a variety of formats. You can download this as a shapefile, as a geodatabase, basically any of the file formats supported by the OGR to OGR utility. So if that's the case, if it's a data download request, then the PHP program doesn't query the database. Instead, what it does is it takes it queries the database, gets the results back for the data to be returned, then pumps them through to OGR to translate into the returned format, and then that data a link is then provided in the web page that's returned back to the browser for the user to download the data or file off the server. Hopefully that's at least vaguely clear. All right, so that's all very well. Now, it works. That's the first web application I've ever written, and it's the first web application I've ever written. I thought it was not bad, I'm quite pleased with myself. But there are real issues with it as I built it. So every time we need to do something, basically the request has to go to the server has to do it chugging away, run its program, and send me the HTML page back to update the screen. So every time I do something, there's a pause while the request goes to the server chugs, sends stuff back, redraws the screen. So it's a bit of a stilted user experience. And that's not good, because, I don't know, there's a sort of figure that's stuck in my head, I don't know how true it is, but if you wait more than half a second for a response on the web, you've probably lost half the people trying to access your web page. Now, how true that is, I don't know. That figure is, but the principle is really strong, that if your web page is not responsive and your website is responsive, and you've got users who can go elsewhere to do the same thing, if your site is not good, they will not use it. So if you're in a commercial business, you need a smooth user experience. The other issue with this model that I've got here is that when I make requests to the database here, it's being done all through, it has to be done. It's done via database drivers. So I have to get what's called a database driver in PHP driver program. That's one of the components, and that driver is what sends the data, the SQL request to Postgres and gets the results returned. Now, only I, who have the password to the Entangle Bank database, can write a database driver or can configure a database driver to access data in the database. You need a user and you need a password to do it. And I don't want to give out usernames and passwords to everybody who might be interested in accessing the data in my database. So as presently configured, the data is only visible to the Entangle Bank application or any other users who have user accounts on the Entangle Bank database. No one else can access the data, for example, to use it in a mashup, to make their own map using that data or their own application using that data. Hence, we need an application programming interface. Okay, let's take a break. Let's take a break there. I think that's a good place to have a break. So, yeah, make it back before past, and we'll finish off. Now, for the practical this afternoon, I don't know whether you know, but the computer science have a new VR suite, virtual reality sort of suite, and they've got an open day this afternoon. I think it goes on from 4 till 7. I'd like to go and see, but I also need to get home, so if it's okay, I'll probably just slope off about 5:30 to go over there to have a look. If anybody wants to come over and have a look, put some Oculus head gear on, and yeah, then you know, come on over. You're meant to get a ticket, but I'm sure you can either order one if you want to go and have a look or not. They're worth a look if you haven't seen them, these Oculus headsets, if you haven't had an experience. So yeah, so we'll maybe finish about half an hour early or sort of practice. Okay, so let's meet up again on the hour. That gives us just over 10 minutes.